The presentation will be in English, but if you have questions at the end, French is welcome as well. So as Christophe mentioned, I'm a worker at NRC. My office is based in Saguenay. We are about 12 researchers over there, and we work a lot on aluminum, but also other materials such as steel and magnesium. So today's presentation is on the prediction of damage of extruded component for crash applications. So first of all, I would like to show you a quick video where we can really appreciate the improvement over the year of the crashworthiness. In this case, it is an overlap frontal crash test of a 1998 Corolla against a 2015. And in this video, you will see that airbags is, of course, a major improvement, but I want you to pay attention to the deformation of the vehicle and compare how the 1998, there's much more intrusion in the occupant compartment. And in that case, for the 1998, as you can see on the video, the energy of the crash exceeded the strength of the vehicle frame. And there's significant intrusion, and even the dashboard is pushed against the driver. So today, even though we have got good accuracy and good design today, there's still improvement to be done due to the lightweighting requirements, but also with the arrival of the electric vehicles that are significantly heavier than standard gas with gasoline engine. Standard car with gasoline engine. So in our case, we're focusing on extrusion, aluminum extrusion. So the most common extruded component for crash application are now designed for two types of crash. In the event of a front crash, the role of the bumper is to transfer the load to the crash box, where the kinetic energy will be transformed mainly into plastic work. So here's the crash box in a vehicle. And for this type of component, soft alloys are normally used to design this crash box due to the high level of deformation to absorb the energy. And in that case, while the crash box is folding on itself, the bending mainly strains the material in the extrusion direction. Event of a lateral crash, it is more the side seal, the rocker, or the door beams that will behave as energy absorbers. These material will, in this case, strains mostly in the transverse direction. And this is more particularly true for the inner webs of the extruded component. And for these lateral crash extruded component, medium to high strength alloys are normally used, since these components are also for structural, and also the space to absorb the energy and avoid intrusion in the vehicle is very limited. Nowadays, many vehicles are equipped with camera and sensors, and the car can attempt to avoid a frontal impact by applying the brakes. Audi and Mercedes, on their side, they developed a kind of active suspension with the lateral sensors that they are able to predict like the arrival of a car and to raise the vehicle quickly in order to have the impact more towards the side seal. And this will reduce the intrusion into the car and the injury to the occupant. However, for let's say less luxury vehicle, we still need to look at the design of the door beams, and in order to reduce the intrusion in the vehicle, but also to have a good load transfer to the A pillar and the B pillar of the vehicle. So this is the outline of my presentation for today. So I will start with the, I think there's kind of a, okay. not to have this all the. Do you see the red line on the screen?
Oui. Est-ce que c'est un PDF? Peut-être que tu l'as écrit.
C'est une présentation, sauf que je pense que j'ai dû écrire en faisant le.
Si tu sors du mode présentation, peut-être que tu peux l'effacer, peut-être.
Très bonne idée. Non, ça doit être dans le... Bon, attendez. Oh, on devrait être correct maintenant.
Oui.
C'est bon. So we will start in this, so we apologize for the delay. So this is the outline of my presentation. So we will start with the evaluation of the material for crash performance. We will continue with the prediction of crash performance with the finite element method, how to predict the plasticity, and we will continue on the prediction of the ductility over material. We will look at few applications to look at the crash performance with the finite element method. And we'll end this presentation with further improvement in estimating the mechanical properties. So most of the automotive extruder are nowadays required to test their profiles at every given amount of extruded material. Normally, a crush test is often required for the production of crush box. So this is an example of a test that is normally executed on the extrusion floor plant. You saw that there was a hole at the top, if I go back, and this is normally used to produce the initial fold at the top of the tube in order to get the correct buckling behavior. So once this test is done, the objective is to look at or to rate the level of cracking with an actual crush rating table. So this, for instance, this is an actual crush rating table that we developed in collaboration with the Rio Tinto, and it is now used by 2 OEMs today. So by using this table, we can assess the level of cracking qualitatively from grade 1, like no crack, to grade 9, like there's an entire box fragmentation. And the acceptable level of cracking really depends on the OEM. Some OEMs will be fine with some cracking, while others won't accept any cracks. It really depends on their mindset. Also, another type of test or mechanical test that is often requested is a standard tensile test. And from that test, they ask for a specific elongation as a crash ductility criteria. However, if you look at the graph at the right-hand side, you can see that elongation in a tensile test is not a very good criteria because it's an instability point. And this instability point is affected by the strain hardening, but not by the ductility of the material. So material with very good elongation can be bad for crush, while material with very low elongation can be very acceptable and have no cracks. However, after the instability point, the material will continue to strain in the necking area until the final failure of the tensile specimen. And we can then measure what is the fracture strain. It can be calculated by measuring the final fracture area. And the fracture strain parameter is the natural logarithm of the final fracture area over the initial area of our specimen. And as you can see on the left graph, it is a much better parameter to access the ductility for different types of alloy. In this case, we tested for 5 different alloy. So the amount of failure strain value follow well the qualitative crush rating. Due to the high ductility of the extruded material, it is very recommended to use the a digital or a macroscope and an image analysis software in order to measure what is the real final fracture area and not use a caliper in that case. It is really due to the higher strain that you reach with extrusions with post after the necking of the profile. The mechanical test that is more and more requested is the VDA bend test. Shortly, it is a 3-point bend test, but with a very sharp punch ridges, and that allow to have a plane strain condition of the outer fiber of your material. And this is used, for instance, to represent the folding behavior of a crush box. So during this test, the punch load is measured, and also the punch displacement. And once a certain level of, let's say, a load drop is reached, cracking is considered at the outer fiber of the material, and it is often the case. And these graphs show, for example, for 2 different types of alloys. So you have a 6061, 6082, which are very common extruded alloys. And you can have, and we did the VDA bend test for 2 directions, so the transverse direction and the extrusion direction. And for both alloys, you can see that there's a significant difference. When you do the bending, the transverse direction, you have higher bending strength, and you will have less ductility. And this is always worse for 6000 series. It is always worse for the for the fully recrystallized alloys such as 6061, 6060, 6063, and you will get better transverse bending with the fibrous materials such as 6082 with some level of dispersed words such as manganese and chromium. But with these tests, we start to see the very anisotropic behavior, mechanical behavior over aluminum extrusion. And due to the significant difference in both directions, further investigation were done for the lateral crush of aluminum extrusions. We started to, by designing a profile that would be appropriate to look at the lateral crush mechanical behavior. So we picked a single cell profile, and we defined the dimension and thickness in order to get the required extrusion ratio, because we were using a small extrusion press, so a 4-inch billet at Rio Tinto. And we also play with the radius at the corner in order to get the required crush behavior. And as you can see, when we use a too large radius, we don't get the behavior we wanted. So we put the minimum radius we could. So we put a 1 millimeter, because when we extrude strong material, having too tight radius will lead you to speed cracking when you extrude. So a radius of minimum radius of 1 was set to the profile. And you can see that also by using this minimum radius, we have much more energy absorption, and we have different folding in the transverse direction as we wanted to have in order to study the lateral crush behavior. So to extrude this profile, we ordered a 2-bridge die, and we put the longitudinal weld on the smaller with it. And the reason why is we wanted to have a sound material in the region of interest, which was on the 50 millimeter length. The lateral crush setup, very simple. So we use a 50 millimeter punch diameter crushing a 200 millimeter tube. The top of the tube was fixed at both ends in order to increase the level of strain experienced by the upper surface. And this is to have a better comparison between soft and medium strength extruded material. So we carried out initial tests with the soft alloy 6063, and we got the required, let's say, mechanical behavior with multiple internal and external transverse bend, as we desired to study these materials. Well, like the axial crush test, we build a lateral crush writing table This was developed to assess again the level of cracking of the various folds, since each fold will give you a different level of strain. And again, the crush quality was compared with the fracture strain, where it is here. So the crush quality was compared with the fracture strain, where we got again a good correlation with the 4 different alloys. So now, since this parameter, the true fracture strain is rarely relevant to assess the level of ductility for both type of crash, so front and lateral crash. Let's have a look at the extrusion parameter that affect the failure strain. Of course, beside the alloy chemical composition. So for a given profile, aluminum extruder are often required to reach a strength and ductility levels. And beside the choice of the alloy, the extruder can play with mainly 2 parameters. So you have the quench rate after the press, which will most likely affect the grain boundary precipitation and precipitate free zone in your material. However, let's say, if you want to improve the crash ductility, as you can see, the failure strain will improve significantly with the quench rate, starting with the quench rate of 50 Celsius per second up to very high. You get a very improvement in ductility. However, increasing the quench rate is very often problematic due to the profile distortion, and it is not a preferred solution. Even 50 Celsius per second is a quench rate that can be problematic for a complex profile that is nowadays designed for the automotive industry. So what's left for the extruder? So he needs to modify slightly the aging treatment, particularly when the level of ductility is not reached at the peak condition. So overaging is often necessary. So if you can see that if you overage your material for different alloys, you always get a higher fracture strain, but at the cost of the yield, of course, there's always a trade-off. This trade-off can sometimes lead to low strength of your material, and then you need to be back to your design phase, of course. So now the question is, even if we have this parameter that is helpful, this level of fracture strain really depends on the geometry of the profile. And it is really difficult at the design phase to select the proper level of fracture strain in advance. And this is even more true for a profile like this, where you have multi-hollow profile, such as bumpers, even the crush box, you often have inner webs and side seal as well. And the issue is we always quench the outer periphery of the profile, so the inner webs will have a significantly lower quench rate than the outside of the profile. As you can see here, the quench rate is significantly lower at the middle as compared to outside surface, and this will most likely be significantly lower ductility and strength as well. So there's a need for a better tool to predict the crash performance of a specific geometry and to select the appropriate alloy, quench rate, and aging heat treatment at the design phase in order to be able also to optimize the product crush behavior. Now, I'm sure that many of you are used to the finite element method. I think that's a method that is used a lot and also teach at the university, at least for the linear method with the hook law. But in this case, we need to look at how to model the large deformation in a crush. And to simulate the large deformation in metallic material, von Mises is the most common yield function, or it can be called also the flow rules. And most of the finite element users are using this function, as it is easier to implement in finite element code, and it has a fast computation time. However, the issue is this yield function was developed mainly for steel industry, and it is an isotropic function. And what it means is the material will have the same mechanical behavior, whatever the direction that you will strain or pull or apply a load to the material. And this is far from being the case for extruded aluminum, as you already see with the VDA bend test. And we need to use a more complex flow rule. In this case, we decided to go with the yield 2004 criterion, which was developed by Béland. And if we look at the two flow rules, the yield 2004 compared to the von Mises, you can see that the yield is more like Tresca. We know that the mechanical behavior of 6,000 alloys looks like more Tresca in most of the cases. So that's why we went with this function that we were able to modify depending on the anisotropy of our material. So quickly, just a few words on how these flow rules work for the people that don't know. In the case of a large deformation world, when the principal stresses are inside the surface, the material is considered fully elastic and the UCLA is applied. But once the principal stress will reach the surface, the material will start to yield and the surface will grow to the next point, and this will depend on the strain hardening of your material. In this case, I illustrated an isotropic hardening. What it means is the wall surface will grow proportionally in all the direction, which is not always the case for all the material, but in our case, we went with the isotropic hardening to simulate the crash, and you will see later what we get from that. It is also an associated flow rules that many flow rules are now developed with non-associated, but we kept the associated flow rule, and we can apply then the normality rule. And what it means to apply this normality rule is we can calculate the strain direction with the normal direction to the surface. So we can calculate what is the slope and at the state of stress that we are calculating, and then know by doing by finding the normal direction, what is the direction of the strain vector. So now we need to calibrate this yield function for von Mises. For von Mises, it's very simple. We need one time cell test. Just need to know what's the yield strength of the material, and it's done. In the case of the YLD 2004, it's very different, and we need to carry out various mechanical tests to calibrate the yield function. In our case, we decided to do various time cell tests in various orientation because it's the simplest way to calibrate this. So all we need to do is we cut time cell samples in the extruded section, and we apply a speckle paint, and we were going to use the digital image correlation to measure the deformation of the surface. And by measuring the deformation, we can calculate what is the commonly called R value, which is it's a parameter to look if the material will strain more in the weighted direction or in the strain direction. So in the case of aluminum, most of the time the R value is low, and that's why we have less ductility for stamping processes, for instance. So how we calculate these R value from the digital image correlation software, so we can measure what's the epsilon x, so the strain in the x direction and the strain in the y direction. And then with the volume conservation law, we can find what's the strain in the thickness direction and calculate the R value, which is called also Langford coefficient in the vector. And another piece of important information that can be also extracted from these tensile tests is the stress ratio, so that at every orientation we can compare what is the flow stress at this direction divided by the flow stress at 0 degree, which is the extrusion direction. So to give you an idea of just the level of strength, vary as a function of the orientation you're pulling your sample. What is great with the 6000 series is also it has a very low strain rate sensitivity. So in our case, we didn't go with very high speed testing. As you can see here, it's from SIBLab in Norway for the 6082. So they carry out tensile tests up to 900 per second, and the strength is very similar in the same range, maybe 5 or 10%. So what's the benefit of having this behavior is we can carry out standard tensile tests and don't have to use strain rate sensitivity plastic law with that. In our case, we use a 0.5 per second speed to test our material. So this is the YLD 2004 calibrated for each point that we measured from our tensile test. So we did tensile tests at every 15 degree. And as you can see, oh yeah, I forgot to mention that the alloy we picked is the 682T6. It's the fibrous material that we extruded. And we did the tensile at every 15 degree, as I mentioned, and we calibrated the flow rules. And you can see that this material, this extruded material, has a very strong anisotropy either in strain. And this is really because of the fibrous structure of the alloy, and it is worse than the fully recrystallized alloys, and the one that is more difficult to work with. Another thing is we can use the VDA band test that we carried out to help on the calibration of our yield function. For example, if we pick the difference in terms of strength from the yield in the transverse direction divided by the yield in the extrusion direction, we can play with the yield function in order to get the correct point at the plane strain location. So we can calculate what's the equivalent stress at the plane strain when the epsilon2 equals 0, and the equivalent stress at the plane strain when epsilon1 equals 0. And if you divide the two equivalent stress, it has to be the same as the division of these two curves, which is the case. For instance, if we pick the extrusion direction VDA bend test and we multiply by the equivalent stress 2 divided by the equivalent stress 1, we get about the same flow stress for the transverse direction. So this is type of thing you can use to better predict the material behavior, which is very important because for front crash, for instance, you have a lot of plane strain deformation. So if you are very accurate for tensile at every direction, but you don't take care of your plane strain direction, it can be problematic. So now let's look at how to predict the ductility over material. So to predict the damage and failure of the metallic material, a failure model is used. There's few damage evolution models that are available in commercial code. You have Lemaitre, Johnson Cook, Gerson, Gizmo. And these are not very complex to implement, but the difficulty is more to find the parameters to calibrate those models. And they are significantly more complex to determine than the plasticity. In our case, we went with the LS-DYNA Gizmo damage model. The way it works is the damage is is incremented for at a given time step. And how to the damage incremented by looking at what is the strain increment for the current time step, and also what is the failure strain at the stress state for the current time step. And this failure strain as a function of the stress state, this is what needs to be calibrated. And the way how we calibrate this is we build this type of surfaces where the state of stress can be defined by two parameters. These parameters are often used to define the state of stress because they are derived from the invariant of the stress tensor. So you have the triaxiality, which is the hydrostatic stress over the equivalent environmental stress, and it gives you an idea of your type of let's say deformation your material undergoes. So is it a tensile, equiaxial, shear, bending, deformation? The load parameter has a higher effect at low triaxiality. This parameter is more used to detect which kind of to know which type of shear deformation mode is done when you do shearing and deformation and compression. So the objective now is to build this failure surface and do different type of mechanical tests and find what is the failure strain as a function of the stress state. And yeah, of course, when the failure of the element or of the one-point integration is always considered completely fail when the damage is equal to 1. So to calibrate this with our 682, we evaluate the ductility with a special type of specimen geometry. It's called a butterfly. This was developed by the Massachusetts Institute of Technology. The biggest benefit of using this type of specimen is that it can be tested in various orientation. And the failure is always located in the middle of the specimen, so it makes it easier to be analyzed. However, one primary disadvantage is that the material ductility is always evaluated in the middle of the thickness. And for instance, for the 682, it can be a little bit problematic because you have small PCG, so peripheral coarse grain layer that will not be taken into account into your ductility model, of course. Also, nevertheless, so to test this butterfly specimen, we built a custom tensile test setup. And we are able to change the specimen orientation by rotating these wheels, and then change from a triaxiality of about minus 0.1 up to 0.9, and various load parameter that can be assessed. So the ductility will be very different, as you can imagine. These type of specimen, when pulled in the 90-degree direction, will fail much earlier than specimen in the shear and compression mode. Now let's see how to evaluate the strain to failure for each of these orientation. So for each butterfly specimen, they are all simulated by applying the corresponding displacement as was measured by the DIC. So in this case, the DIC is not used to measure what is the failure strain, but is rather used to measure the displacement on 2 planes, and we apply the exact same displacement to a mesh. And the reason to do that is in finite element, the failure is really function of the element size. So so it's not because you measure a failure strain of let's say 10.1. 10% that you need to apply the exact same in your model, because you need to check if how the element is computed and how the strain is computed in your element. So that's why it is rather better to directly apply the deformation and change the failure surface, or let's say the failure parameter, until we obtain the exact same failure behavior with finite element and as compared to the experiment. So the image on your right shows the experimental curve in black, and the result from the finite element model for a 0-degree orientation. So this is a shear deformation. Once the strain for each specimen orientation is evaluated, a failure surface can be built as a function of the stress state. So this is the failure surface that was developed for the 632 in PKH condition. So we are not done with the damage model. The final step is to calibrate this damage model as a function of the element size. It is very important because larger elements are often necessary to decrease the computation time. And it really depends on the size of the part and also the computer capacity. And so yeah, depending on the size of the element, the amount of strain, and even the local stress states will be a little bit different. And the failure needs to be, at the end, the failure needs to be the same, whatever the type of So in order to do this, we need to scale the failure strain as a function of the element size. This can be also done as a function of the stress state, but in our case, we only pick the tensile specimen, but this could be done, for instance, for the VDA bend test as well, and see if we need to scale differently the failure strain for the same element size for a plane strain deformation, for example. So at the end, when we apply the scaling factor, the objective is to have the exact same tensile curve for all the different mesh size. Yeah, and now, once this is done, we are now ready to look at real application and see how the model behaves. So here we have the lateral crush test. We have the load versus sponge displacement for a typical lateral crush test with the extruded 632 in the PKH condition, which is T6. Typical test is illustrated with the blue curve. And by comparing with the prediction of the finite element model, which is the red curve, we found that there's a very good agreement observed between the two curves. There's also a good agreement for the energy absorption and also for the failure amount and location if you examine the image of the crush profile done by both the experiment and the simulation in red. At the end of the test, the loads decrease more in the model, and it is attributed to deeper cracking of the material at the bottom as compared to the real test. Here it is interesting to look at the effect of the material ductility on the crush behavior by removing the damage option in the model. Where the orange curve is the crush behavior without damage in the material. So by superimposing the curve that includes the damage, the load drops can be attributed to a specific failed region. So here the first load drop is due to the cracking of the first fold at the top of the tube, and the cracking of this fold also shifted the location of the peak load. Afterward, the ductility does not have that much of an effect until the end of the crush, where the loads drop significantly due to the failure of all the other folds. Here we will just have a quick look at the effect of plasticity model use. For instance, if we use an isotropic plasticity model, such as a widely used isotropic von Mises, which is the green curve, the crush load are significantly over-predicted. And the table on the right is the energy absorption predicted by the anisotropic plasticity model used and the von Mises with and without the damage option. And as you can see, for this alloy and temper, for the 682, the plasticity model has a stronger influence on the accuracy of the crush simulation than the damage model, because the finite element model with the von Mises gave a way too high energy absorption as compared to the yield 2004 due to the isotropic behavior that is not taken into account. Finally, we can look at the effect of having larger element sizes. So by using element size that is almost twice as large, the lateral crush prediction is still reasonable with only a slight difference on the location of the peak force. The failure amount and location are similar between the two mesh size. If you look at the profile on your right, the energy absorption prediction is also in the same range. We are now ready to study the crush. With that being done, we are now ready to study the crush behavior of various profile geometry and improve the shape of the profile or test various alloys and tempers that we have already investigated and have in a material database. So for example, here's the lateral crush behavior of a strong 6000 alloy that has a too low quench rate. Here, as you can imagine, the damage and failure model are much more critical than having a very accurate plasticity model. Here's another example of using such type of method to predict the extrusion crush behavior. So electric vehicles being more popular, this is an example of a side seal designed to protect a battery pack. It is a two-component design, so you have a medium strength profile, so a 6082 that is stronger and will be able to transfer the loads to an insert that is softer, but it's gonna reach a higher level of ductility. And we're gonna look at how this profile will behave under a pole crash test as required by the Insurance Institute for Highway Safety. In this case, the speed of the vehicle is not very fast, but that's the test. So it's 30 km per hour, hitting a pole of a 10-inch diameter. So here's the predicted mechanical behavior of the side seal with the failure location. And from this computation, we can have the load versus displacement that was applied on the pole. And from that curve, we can then calculate the absorbed energy. As I mentioned, the electric vehicles are significantly heavier than typical gas-powered car. And if we pick, for example, the Model 3 from Tesla, that has an average weight of 1,700 kilograms. We can calculate with the kinetic energy at the testing speed what is the energy to be absorbed. So it's 60 kilojoule. And looking at the simulation we just carried out on the side seal, we can see that we are near to have a intrusion in the battery pack. Even if the vehicle is not going at very high speed. So I just now would like to show you further improvement in estimating the mechanical property, because it's a hard work to test all the tensile properties and also all the butterfly specimen or whatever types of mechanical tests that needs to be carried out to find the failure surface. So you have so many different types of alloys and quench rate as depending on the extruder's capability and also aging treatment. So it means a lot of work to build all the material database. And now we are looking at how to how to find those parameters by simulating the whole extrusion process. So for example, here's the box section that we use for the lateral crush. We have the tubular extrusion die, and this is the equivalent workpiece shape. So what it means is the shape of the aluminum inside the die. And what we do is we simulate the extrusion with the commercial code Alter Hyperextrude. And after the simulation of the extrusion, we can compute the strain and temperature history for various streamlines from the back of the billet up to the exit of the die. And by having the strain and temperature history, we can add this to a crystal plasticity model, and we can find a very good agreement of the final crystallographic orientation as a function of the position inside the final extrusion. So this is the crystal, for example, the crystal of orientation from ABSD, the one that are not very known to ABSD is a technique that is used to find the crystallographic orientation at each grain, at various grain in your material. And we can plot PO figures like that. And if we compare with the crystal plasticity model that we developed for extrusion, we found a very good agreement. And now the next step is to use this prediction with crystal plasticity in order to define what is the parameter that we need to use for the yield surface. And at the end, for example, find differences like I'm showing at the right. So this is a strip extrusion that we did for the 6063 and also a box extrusion. And here are the length forward coefficient as a function of the testing angle. And you can see that for a flat strip, the R value are very different from the box section. So at the end, the objective would be to be able to predict that directly from the modeling of the extrusion and the crystal plasticity, and also applying the crystal plasticity model to find what is the correct stress and strain anisotropic behavior of our material and fit that into the yield criterion. And the last step, of course, the crystallographic orientation is not sufficient to know what's happening in terms of strength and ductility. So we need to look at precipitation models and evaluate what's the level of strength and ductility depending on the precipitation that occurs in our material. For instance, what is the precipitate free zone after the quenching? And to build that, to study that, we design a quench simulator, which is an induction heater that will heat very quickly and precisely a piece of extruded component. And afterwards, after a certain amount of time for solutionizing the precipitates, we can control the quench rate with the nozzles. And then afterwards, we can test what's the final property of our material, and in an attempt to calibrate the precipitation model as a function of the strength and ductility. So this is what we are currently doing in order to improve our capability to predict the crash behavior. And also what has to be kept in mind is depending on the complexity of the extruded profile, the mechanical properties will be very, very different. And they are also different in the thickness because there's a lot of shear near the surface when you extrude. So the texture and also precipitation is different near the surface as compared to the core of the material. And this needs this in the future, we hope in the future to be able to take that into account with this type of work. That's it for me for today. So if you have any questions, it's a pleasure for me to answer.